So, good morning to all. Today we will continue the same lecture, that is yesterday last class we started talking about one example. Okay. So, let us move back the example here and see this is a program. Yeah, let us read this problem. So, a computer has separate data and the instruction cache. Data cache has 8 blocks. Okay, and each block can hold one word of 16 bit. Number of set is 2. If set associative mapping is used, consider the main memory address is 16 bits. Okay. And then there are program here, basically this program normalizing the first row. Okay. Consider the array A is organized in the column order and the first element, that is A00 is located in A7 A00. Okay. It is in hexadecimal, as you can understand. So, that the cache content if we use different mapping scheme. Okay. So, this was the problem, and now what we should do it, if there is a replacement policy. So, replacement policy is nothing but the LRU, and then with along with that we have the different mapping scheme. So, then you have to show the cache content. Okay. So, this is the problem. So, we started with here. So, in case of the direct mapping, say memory, first what we do it, we store the content or the array content in the column order. Okay, column order. So, therefore, A00, then A10, A20, A30, again A01, A11 and so on. So, it started with 7A00 and 7A01, as you can see. Now, if we use the direct mapping, so first is for direct mapping, we know there are three different type of information required. So, first one is the word, but within a block, as you can see, there is only one word. So, therefore, there is no need for keeping any other bit for identifying the words within a block. Okay. So, therefore, W is 0. So, then there is something called tag. Okay. No, first in direct mapping there is word, and then you need the cache line. So, there are 8 cache line. So, therefore, to identify the 8 cache line, use log 8 base 2. So, therefore, 3 bits. Okay. So, therefore, this 3 bit will identify the cache line or cache block. Okay, and rest will be the tag, that is we have seen in the last class. Next is associative mapping, we have only tag and the word. So, word is 0. So, then entirely it will be tag. Okay. So, that is now we are talking about, in the last class we talk about the direct mapping, now we will talk about the associative mapping. Next we will come for the set associative mapping. Okay. So, here is the program. Okay. And then we have seen the cache content. Okay. This is for the direct mapping. Okay. This is for the direct mapping. Okay. So, direct mapping is you go to the program here, first is j equal to 0, j less than 10, j plus plus. So, first is sum is 0. So, these are the variable is there already in cache, you assume. So, A00, where is that A00? A00 location is here 7A00. Okay, that is you can see here. So, now what you have to do, if you use the direct mapping, first you identify the cache line. Okay. So, for cache line, that last least 3 significant bit. So, least 3 significant bit indicate that cache line, that this content, that A00 must be placed in the cache block 0. Okay. So, therefore, we write it A00. Okay. So, next is what A00, then it will be A01, right. 01, where it is there in the main memory, you just go. So, in the main memory 01, right, 01 is here because it is in column order. So, if you have the array like, see, this is 0 row, then it will be 0, this will be 1, this will be 2, this will be 3. Okay. And if it is column order, so there are 3 cross 4 into 10, total elements, right, array size. So, therefore, so this is 0, first is 0, then this will be 1, this will be 2, this will be 3. Okay. So, this is 4 up to 10. So, now entire first column will be in the consecutive memory location, as you can see here, you can see here, you can see here. Next it will start 0 1. So, 0 1 is in the location that is 1 0 0, that in the 7 A 04. So, 7 A 04 if you identify, so least significant bit is nothing but 1 0 0. So, therefore, this block, that is A 01 must be in the block 4. So, that is we wrote it here. So, in the block 4 A 01 will be there. So, next which memory location should be accessed, because we are accessing row, next will be A 02. So, but A 02 where it will be there, you have to identify A 02. So, it was 00, 01, then 02 where it will be there, 02 will be in the location 100, because this was 4, 5, 6, 7, 8. So, again 000 means that is the least 3 significant bit. So, it will be again block 0. So, but block 0 is already, it had the value. So, therefore, you need to replace it. So, if you move again, so block 0, right, block 0 is already 00 is there, then what is the option? You need to write back to the main memory and then you need to place the A02. So, therefore, it is A02. But what is the value of the loop, what is the value of j? J will change from 0 to 1 and then it is 2, j is 2. Now, if again j, when j equal to 3, again you add 4. If you add 4, then what will happen? So, it will come 16 plus 4. So, it will be 20. So, 20 is again coming, last significant bit will be 100. So, therefore, it has to put again 4. So, therefore, it will be in A03. So, that is why j equal to 3. If you keep on doing the same thing, at the end you will get the AJ98. Now, once you complete this loop, you will have the another loop here. Once you complete this loop, another loop is in a different way, that is the starting with 9 and then you move up to 0. So, then 9 and 8, right. So, if you see here 9 and 8, which content it needs? It needs the 09 and 08. So, therefore, if you see here, so A I equal to 9. So, therefore, A09 and next will be A08, but both the content are already available in the, both the content is available here, A08 and A09. Okay. So, therefore, A equal to 09 as same as the I equal to 9 in j equal to 9 and then I equal to, it will be I equal to, it will be 9 and 8. So, this content will remain same, that means cache hit was there, because the content was available here. Okay. So, similarly, if you proceed here, then finally, you will go here and then you need to count that how many times there will be cache miss, and if you see that only, I think the only 2 times there will be cache hit, rest of the time there will be cache miss. So, you can compute the percentage of hit out of it. Okay. So, there will be 20 access, out of 20 there is 2 hits. So, therefore, access hit ratio will be 2 by 20. Okay. So, this is all about the direct mapping, and next we will talk about the associative mapping. Okay. So, next we will be talking about associative mapping, and this is placement. Okay. So, then you consider the same scenario here. So, this is block number in cache. Okay. So, let us say this is 0, this is 1, this is 2, this is 3. Okay. Okay. So, now you go that we are talking about associative mapping. Okay. So, here we go. So, j equal to 0. So, therefore, a 0 0. So, if a 0 0, then where do you place? In associative mapping, there is no question of place fixing the place. If there is a space, so you keep anywhere in the any cache line, right, and then there is no what is called is word odd bit. So, W is 0. So, therefore, all will be tag only. So, therefore, A00, A00 as you know that A00 is placed in the location 00. So, therefore, so this block will be anywhere in the cache line. So, therefore, what we do it, we can keep with j equal to 0, we can keep anywhere in the cache line. So, we can keep anywhere A00 here. Okay. Next, you increment the j. Okay. So, increment the j, so j will be 1. So, where it will be there j 0 1. Okay. So, 0 1 means coming here, but as you know that for associative mapping, so there is no question of displacement or there is no question of the odd. Okay. So, therefore, this is 0. So, entire term will be, entire bit will be tag, and you can place anywhere in the cache line. So, therefore, for our simplicity we are placing here you can place anywhere. So, we can write it A01, but it could be written anywhere in between 0 to 0 to 7. So, therefore, j value will change here. So, j will be 1. Now, you increment the j. So, j will be what we are doing basically, if you see here program is sum equal to sum plus A0j. Okay. So, therefore, what we are doing sum equal to sum plus A0 j, and j are we are incrementing starting from 0. So, then 0 1, now if you increment j equal to 0 2, so now you change the value j equal to 2, then what will happen A02, A02 location is already we know in the main memory, yeah. So, in 02 we know in the main memory 02 is here, but as you understand that there is no displacement or the odd bit. So, therefore, the tag will be entirely, the entire address will be the tag, and we can place this one is anywhere in the cache line. So, therefore, we can write it A02, and then we increment the value j equal to 3. Next is A03, we can keep anywhere wherever is available. So, we write it 03, next 04, A05, A06, A07. Okay. So, then j value is now 7. Okay. So, last j value was 7. Now, we increment the value of j. So, then A08. Okay. So, now there is no space in the cache memory as you can see. So, then what you need to do? You need to apply the LRU replacement policy. So, LRU replacement policy I taught in the last class. So, that page which has been used recently, that page should be replaced. So, therefore, just now that which page is used, that is 07. So, before that which page was we use 06, before that 05, 04, 03, 02, 01 and 00. So, 00 has been used referred long before. So, therefore, that victim page should be 00. So, we should replace the page 00 by. So, therefore, this space will be replaced and the value j is 8. So, this will be replaced here. Okay. It will be A08. Okay. And then rest will be the same. So, I may write it here. So, A08 and this will be remain same A01, A02, A03, A04, A05, A06, A07. Okay. So, now after j value j is 8, now you need to have A09. So, there is no space here. Okay. As you can see, this is cache is full. So, then you need to apply the LRU policy. So, this page was used just now referred, before that this one, before that this one, before and A01 was used long before. So, therefore, what you have to do, you replace only A01. So, it will be A09 and then j value will be 9. So, this way we can complete the first loop. Now, you move to the second loop here. So, this is completed, right. Now, second loop is started with a equal to 9, okay, and then we are doing some operation. So, that means now the loop is remain same, similar type, okay. A0 I will start with say we need to have the value a 0 I instead of j. Now it is coming a 0 I, okay, and you have to start from the loops will start from 9. So, therefore, first is a 0 9, whether it is there in the cache, it is there. So, therefore, cache hit. So, hit is 1. Next is increment the decrement the value I will come down to 8, this is also there. So, then there will be one more cache hit, then you decrement the value 7, 7 is also there, you decrement the value 6, this is also there, 5 is also there. So, you increment. So, this is 7, this is 6, this is 5, this is 4, this is 3, this is 2, this is 2. Then after, so therefore, last value of I in this situation, that is I equal to 2. So, this will remain same here, assume these values are same here, I am not writing here. So, this is the same value. So, I value is 2. Now, you decrement the value I equal to 1. So, there is a full of the cache. So, therefore, cache miss, and therefore, you need to apply the LRU page replacement policy. So, LRU page replacement policy, which page was referred last, that was the page, that is the page 2. So, you cannot replace, before that it was 3, 4, 5, 6, 7, 8. So, that page has been referred long before. So, that is 0 9. So, therefore, you need to replace 0 9. So, therefore, A 0 1 and this will be A 0 8, this will be the same, this will be same, this will be same, this will be same, this will be same. Okay. Now, again you change the value, you need to update decrement the value I equal to 1. So, I equal to 1. So, this was A 0 1, okay, that is the okay. So, A 0 1, okay. So, then all will be same, all will be same, all will be same, all will be same here. Now, I will be 0, I will be 0, there is no, so there will be cache miss, and once cache miss, so you need to apply LRU page replacement policy. So, which was the oldest page? So, oldest page was A08, it is not oldest page, which was the page which referred longest period of time. So, that is the A08. So, therefore, you replace A08. So, A08, so therefore, you bring instead of A08 A00, this will be A01 and then this will be same, this will be same, this will be same. Okay. So, this is for the associative mapping, and then you start counting how many times hit 1, 2, 3, 4, 5, 6, 7, 8. Okay. So, then hit ratio will be 8 by 20. Okay. So, in direct mapping we found that is 2 by 20. Okay. So, now we will be talking about set associative mapping, and if you move back, we said there are two sets, right, somewhere we said, right. So, in the problem we said ki there are two sets. So, how many blocks are there? There are 8 blocks in the cache, or that there are 8 cache line and 2 sets. So, therefore, in each set there are 8 blocks. Okay. Each sets there are 4 blocks, right, in each set. So, therefore, what will be the cache content? Okay. So, here now we are talking about set associative mapping along with LRU page replacement. This is replacement and this is placement in cache, this placement from cache. Okay. So, we do the same thing here. So, block or cache line, okay, block number. So, we are using set associative mapping. Okay. So, therefore, 0, 1, 2, 3, this will form a set, let us say set 0, and then 4, 5, 6, 7, this will set 1. So, therefore, in set associative mapping, as we know, we should have three different type of bits. One is odd, in this example this is 0, and then there should be what, set number, and then rest is tag. Okay. So, therefore, if you move back here, what we can see here, in case of the set associative mapping, word is 0 and then set. How many sets are there? There are 2 sets. So, you need to identify the set by single bit. So, therefore, this will be tag and then 1 will be the set number. So, in this example let us say we start with first one. Okay. So, therefore, this last digit least significant bit here. So, this is least significant bit, this will identify the set number, right, and then rest will be, so this entire thing will be tag. Okay. So, this is tag and this one is the set number. So, therefore, for any element first we see what is the address of that element and we will see the what? We will see the least significant bit. If it is 0 then it will be assigned to set 0, if it is 1 it will be assigned to set 1 and within the set we can place anywhere. Okay. But obviously, we should follow the replacement policies when we need to replace it. Okay. So, therefore, first is as you understand the program, we started with j equal to 0 and then the memory element is A00. So, A00 location is here 7A00 and what is the least significant bit? So, 0. So, therefore, we should place this A00 in set 0. Okay. So, therefore, A00 must be placed into, so maybe we can write it here, that is j equal to 0 and in a set 0 and we can write A 00, but please note that you can write anywhere 0, 1, 2, 3 anywhere you can write. So, I wrote it A00. Okay. Next is A01. So, where is that A01? So, A01 as you can see A01 is here. So, that means every 4 starting with 00, then you add 4 you will get the address 100, you again you add 4 you will get the third element, again you add 4 you will get the fifth element, okay, sorry fourth element, again you add 4 you will get the fifth element and so on. Okay. So, starting with 00 here 00 you add 4 that is 100, so address will be 100. What is the least significant bit? That is also 0. So, therefore, for this second element of the array also will be placed in the set 0. So, then you place here in set 0. So, and you can keep anywhere if there is a space. So, you write A01. Next will be 02. Where is 02? You go back here. Okay. 02 is here. Again how? You just simply add whatever the last element was there, you add 4. So, you will get the next element. So, it was 00, then 100 you add 4, again you add 4. So, then you will get the 8. So, that is the we can see, and then what is the least significant bit? Again 0. So, 8 plus 4 12. So, again least significant is 0, 12 plus 4 least significant is 0. So, therefore, it will be always map into the set 0. So, therefore, A01 then you write A02, then you write A03. Okay. Now, the value of j change, this is 0, 1, 2, 3. So, this is the output after j equal to 3. Okay. So, next you have to increment the value, as you see in the code it was sum equal to sum plus A0 j. Okay. So, j value is 3. Now, you increment the value j equal to 4. So, j equal to 4 means again you add 4. So, therefore, last digit again it will be 0, it will map to the set 0, but there is no space. If there is no space, then you apply the LRU page replacement policy. So, LRU page replacement policy says that you need to replace the page, you find the victim page which has been referred long before. So, therefore, the page here see just referred is 03, before that 02, before that 01, 00. So, that is the victim page is now 00. So, 00 has to go out from the cache memory. So, therefore, that A this will be 0 and then this will be what 3, this will be 04. So, therefore, obviously there is miss, there is no hit in the beginning also, then 04, then again 05, which one will go away? So, this will be the remain same, this will remain same, this will be remain same, and the value of j is changed to 4. Okay. Now, you increment the value of j equal to 5, that is not in the cache. So, you have to bring it, where do you place it? Again you add 4. So, therefore, address will last bit again it will be 0. So, 0 means again it will map to the set 0, and then you can place anywhere, but there is no space. So, therefore, you have to use the ALU page replacement policy. So, ALU page replacement policy will replace the page A00, but that page was referred long before. So, therefore, again you replace here instead of 01, so you put it 05. So, then this will be 03, this will remain as 04. So, this is up j equal to 4. Now, you increment the value j equal to 5, again there is no space. So, this is 4 3, this will be the, this will remain same. So, here you write a 0 5, again this will remain same. Now, you increment the value j equal to 6. So, j equal to 6 means you have to replace here j 6, this will remain same, a 03, a 04, right. So, this is 04, this is 03, this is 05, this is 06. Okay. Now, what will happen? Now, you again j equal to 6, this is change. Now, you change j equal to 7, there is no a 07. So, therefore, what you have to, and then this is full. So, then you apply the page replacement policy, this is referred just, this is referred just, before that this one. So, 02 was the page, or 02 was the block which has referred long before. So, therefore, you replace then again 02, right. What is the 04, right, this is 04, this was 03 or what. So, then 03 will be replaced here. So, that is longest page will be referred. So, therefore, you change j equal to 7, okay. Then you change j equal to 8, j equal to 9. So, j equal to 9 means this will be there, j equal to 9. So, j equal to 9, this is what 6 5, these 2 will go, j equal to 8. So, you can write anywhere. So, j a 09, a 08, a 07, a 06. So, this is 6. Okay. So, this is 6, okay. 9 8 7 6, j equal to 8, j equal to 9. Now, that loop, first loop is completed. Now, you come to the second loop, that is starting with I equal to 9. So, 09 is there. So, hit. So, you count hit 1, 08 is there. So, you count hit, 07 is also there, you count hit, 06 is also there, it is hit. So, this will be the remain same, a 06, a 07, a 08, a 09. So, this will be all hit. Okay. So, value will change from I equal to 9 to up to 6, this is 6. So, value will change from 9 to 6, and then there will be 4 hit. Next, j equal to 5, again there is no space. So, you apply the page replacement policy. So, which one will go away? 09 will go away. So, here it will come 05, and this will remain same, this will remain same, this will remain same, and I equal to reduce to 5. Then I equal to 4, then which one will go away? So, a 08 will go, I equal to 4, this will a 05, this will replace by 04, this will remain same. So, it will be a 098, yeah, 7, a 06. Then I equal to 3, I equal to 3, which one will go away? So, this is 6, right, this is 6. So, oldest is 07, so this will go away. So, a 03, a 04, a 05. So, now you decrement it 2, so this will be replaced by 0, 2 and so on. So, number of hit for this one, it will be, hit ratio will be 3 by 20, 4 by 20. Okay, we conclude today's class.